This video is about learning outcome number 1, which is all about describing and creating 7 types of common graphs that are used to visualize data. So the first type is a dot plot. A dot plot is a graph of quantitative data in which each data value is plotted as a point or a dot above a horizontal scale of values. Dots representing equal values are stacked. So we're going to see something like this. It looks a lot like a histogram, but instead of separating our data into a number of classes, each data point is represented as a dot. Now these are pulse rates of males, and all of the values that we have for those pulse rates happen to be even. I believe this data was collected by taking someone's pulse rate for 30 seconds and then multiplying by 2, so we got a bunch of even numbers. Now each of these dots represents a single pulse rate in our sample. So this is a single pulse rate of 40. Then we had one man in the sample that had a pulse rate of 42. There were 2 men that had a pulse rate of 50. There were 5 that had a pulse rate of 52, 6 that had a pulse rate of 54, 2 that had a pulse rate of 56. I don't know how many dots that is. 1, 2, 3, 4, 5, 6, 7, 8 men that had a pulse rate of 58. And then 7 men that had a pulse rate of 60, and so on. So if you look above a value, like above this 80 right here, you see the number of men that had a pulse rate of that value. So we have 1, 2, 3, 4, 5, 6 men that had a pulse rate of 80, 1 man in our sample that had a pulse rate of 90. That's a 92 pulse rate, that's a 94 pulse rate, and these two together are both 96s. And it looks like we also have 1 guy in the sample with a pulse rate of 102 and another one with a sample or a pulse rate of 104. And you can tell all of that from just this very simple graph, which just consists of this horizontal axis and a bunch of dots above it. So here are some features. This is nice because it displays the shape of the distribution of data in much the same way that a histogram does, except it's much more specific, and I like that. Because we can see that each of these dots is directly above a number. And we can also see, due to the spacing, that this is 50, 52, 54, 56, 58, and 60. You can see that these are these are in multiples of 2. You're able to recreate the original list of data values just by having this picture. So it's like a histogram, but it's even better because all of the data is actually in there, just represented by a single point. I think that that's really beautiful and elegant, very elegant way to share all of that information in a quick picture. So that's the first type of graph. The second type of graph that we're interested in is a stem plot. You'll probably see this a lot in your classes, especially if you're a social science student. Sometimes stem plots are called stem and leaf plots. These represent quantitative data as well by separating each value into 2 parts. There's a stem and a leaf. Often the leaf is the rightmost digit or the rightmost 2 digits or something like that. And the stem is either the leftmost digit or the few digits on the left. So we just take each data value and we separate it into pieces. Often the stem, if we're talking about numbers between 0 and 100, the stem will be the tens place, and the leaf will be all those numbers, those digits in the ones place. So here's an example. This is a stem plot for the exact same data set. It's that data set that consisted of pulse rates of men. So we saw on the dot plot that there was a pulse rate, one pulse rate of 40 and another pulse rate of 42. So that's represented by this 4, that's our stem, and this 0 here means that 40 is one of our data points. And then the 2 here means that 42 is another data point. And then in the next row, we see the stem of 5 and all of these leaves. Notice that the leaves are written in ascending order. So from this, I can recreate the list of data as well. So there was a 50, a 50, 1, 2, 3, 4, 5 52s, 6 54s, 2 56s, and it looks like 8 58s, and so on. Now notice that this last stem is a 10 instead of a single digit, and that's fine. You just have to sort of make sure that you're in the same placeholder. So if this was 40, 50, 60, 70, 80, 90, this is not, you can't have a 10 in that 10th place, but if you were to have a 10 in the 10th place, that would represent 100. So this is okay as long as that last digit for the stem is all in the same place. Now these two numbers, the 2 and the 4 in this last row, represent a pulse rate of 102 from one man and a pulse rate of 104 from another man. So this is giving you exactly the same data, just arranged in a slightly different way. Now notice we've got these features. We see the shape of the distribution of data again, but this time it's kind of sideways. It's like if we turn our head 90 degrees, we see that same shape, that shape of the distribution. If you have a row that has more numbers in it, well, that tells you that there are more men that have pulse rates in that group. It's kind of like the classes in your histogram or the classes in your frequency distribution. If I'm looking at this row where I've got the stem of 6 and all of the numbers after it, that tells me that most of the men in our sample had pulse rates between 60 and 69, and they're all listed here, and we could recreate them if we wanted to. So if that row is longer, that corresponds to higher frequencies, and higher frequencies would be taller bars or higher bars in our histogram. So it's kind of like a histogram just on its side. And again, just like the dot plot, this retains all of the original data values, whereas the dot plot used dots to retain those data values. We're here using actual numbers. And another benefit of having a stem plot, is that the sample data are sorted in arranged order. So you see 40, 42, 50, 50, 52, 52, 52, 52, 52, 52. Like you can see them in order. It'd be very easy to list that sorted data from the beginning to the end, from smallest to largest, by looking at a stem plot. So in this example, we're going to try to construct a stem plot ourselves. This is modified from exercise 7 in section 2.3. We've got pulse rates again in beats per minute. This time they're pulse rates of females. And we're asked to construct a stem plot for the given data. The first thing we want to do, you don't have to do this, but I think it's a great first step, is to take that data and arrange it in order from smallest to largest. So what I'm going to do is I'm going to do this on a piece of paper for you, and then I'll show you how to do it in Excel. It's actually much faster in Excel, but just in case you don't have Excel yet, I'll show you how to do it on paper. So I'll stop sharing my screen for a moment. Oops, my document camera is not turned in or plugged in. It's getting late. I think I'm just tired. There we go. So we want to construct a stem plot first by putting these numbers in order. So I'm going to look for the smallest number on my list first. And it looks like 36 is the smallest number on my list. And then I'm looking for anything in the 40s. I don't have anything in the 40s. How about the 50s? I've got a 56, a 58, a 56. So it looks like I've got two 56s and a 58. Okay, now I want values in the 60s. Smallest to largest, so we'll do 60 first. There's no 62s, we've got a 64. Then we've got two 66s, no, three 66s. Oops, I missed a 64, so there's an extra 64 in there too. That's okay. Sometimes that happens. And I think that's all the ones in the 60s. Now I want to look at the ones in the 70s. There's a 78, and a 76, and a 78. I think that's all of them. So 76 is the smallest. And then we've got three 78s. Okay, now let's look in the 80s. I've got an 80, an 82, an 84, an 86, and an 88. Okay. All right, and then we have the 94 right there. So we've got these sorted in order. Now let's go back to the PowerPoint. Okay, so we wanted to arrange the data in order from smallest to largest. And let's see if we have the same list. 36, 56, 56, 58, 60, 64, 64, 3 66s, 76, 78, 78. Ooh, it looks like I'm missing a 78. Or maybe I was missing it when I wrote it down over here. That's okay. There should be a third 78, but I think I just didn't have it on my list at the top. Then we've got an 80, an 82, an 84, an 86, an 88, and a 94. Okay, great. After you've arranged the data in order from smallest to largest, now you want to identify the stems and list them in a column. Because these are numbers between 0 and 100, the stems will start with 3 and then end with 9. So I'm looking at that tens place. I've got 3, 4, 5, 6, 7, 8, and 9. And then lastly, we want to identify the leaves and list them to the right of the corresponding stem in ascending order. So my leaves are a 6 for the that 36 there. I don't have any for the 4, and that's okay, you just leave it blank. For the 5s, we're gonna have a 6, and an 8. That represents a heart rate of 56, another one of 56, and then another one of 58. Then in the 60s, we've got 60, 64, another 64. Then we've got 3 66s. Okay, now we're on to the 70s. We have 76, so there's a 6 there, then a 78 and a 78 and a 78, so 3 8s. And we're done with the 70s. Then we've got heart rates in the 80s, so that's a 0, a 2, a 4, a 6, and an 8. And then for the 90s, we've got a 94. So that is our stem plot. And that's exactly what I have on my paper. So my paper and my PowerPoint show the same thing. Now, I would like to show you how to do this in Excel. So I'm going to switch to showing you my Excel spreadsheet now. So I'll be sharing my screen again. This time I don't want to show you my PowerPoint. I want to show you something else. I want to look at that pulse rate data. So here it is. Now you're going to like this, I think. So remember what we did to create the stem plot. The first thing we did was we sorted the data. So in Excel, all you have to do is highlight that box, and then in the corner, there's like a little, it looks like another little square, but you want to grab it and then pull down. So you're going to highlight all of your data. Oh no, undo. Why am I doing that over and over again? Okay, now it did what I wanted it to do. Then you want to copy it and paste it. I like to do that just in case I accidentally write over it. I don't want to mess it up. And then just go to sort A to Z. If you click on this, you can sort from largest to smallest or smallest to largest. We'll do smallest to largest. And look, it gives you that sorted list of data: 36, 56, 56, 58, 60, 64, 64, 66, 66, 66, and so on. Exactly the same sorted list that we found by hand. Okay, so now that I've got my sorted list, I'll write my stems down. That's 3, 4, 5, 6, 7, 8, 9. And then we can enter the leaves over here in the column next to it. So we have a 6 and then no leaves. Then we have a 6, whoops, that's a 6 and a 6 and an 8. And then we've got a 0, a 4, a 4, a 6, a 6, a 6. And then we've got a 7 and or 76 is 76, then 78, 78, 78, so that's 8, 8, and 8 as my leaves there. Then in the 80s, we have 0, 80, 82, 84, 86, 88, and then you've got 94. So I know it doesn't look quite right until I change the formatting on those, but now you've got your stem plot right there. It's exactly the same as what we did on the piece of paper. I really like this, using this for sorting. It's kind of silly to do it by hand, and as you've seen me do, sometimes you make a mistake. Human error is very possible here. But when you understand the idea, it really makes sense to use technology, to have technology do it for you. Okay, so those are stem plots. Now I'm going to go back to sharing my desktop again. Oops. Now I want to show you my PowerPoint. Okay. There we go. Now the next type of graph, the third in our series of 7 graphs, is what's called a time series graph. A time series graph is a graph of time series data, which are just quantitative data that have been collected at different points in time, such as every month or every year. It looks like, if I'm looking at this data, this is 1985 to 1990, and there are 1, 2, 3, 4, 5, 6 points, including the endpoints. So it looks like they're collecting data every year. And on this vertical axis, we have law enforcement fatalities. And then it shows how those have decreased over time. Now, I'm not sure where this data came from. I don't know what the source is. I don't know what the units are. I mean, ideally, that would be 180 people and not 180,000 people or something like that, even though 180 people is way too much. But this is a graph of law enforcement fatalities versus the year on this chart here. And if you look at this trend, according to this data set, it looks like the law enforcement fatalities have been decreasing over time. That's what this graph is telling us. Now, time series data, like I just said, reveals information about trends over time. In this video, I'm not going to show you how to create a time series graph using Excel, but it's actually very simple. You're going to be given data sets when you're doing your homework. You can actually download those as an Excel spreadsheet, and then have Excel graph a time series graph like this for you. I show you that in one of the example videos, but I'm not going to show you that within this lesson. So check out that example video if you'd like to know how to make a graph like this in Excel. The fourth type of graph is a bar graph. Now, these are for categorical data or qualitative data. We have bars of equal widths shown in a graph to show frequencies of different categories of categorical data. You can have gaps or no gaps between the bars. Either way is fine. And what's nice about a bar graph is it makes it very easy to compare different categories. Now, Pareto charts are a special type of bar graph. There's just one stipulation. In a Pareto chart, bars are arranged in descending order, so the tallest bar comes first. What's nice about this is that it makes it easier to compare the different categories. And the fact that it starts from the tallest bar and goes to the largest bar draws attention to the most important categories. So it makes it very clear what category, has the highest frequencies. So here's an example, and I actually don't know the source of this data as well. But this is a Pareto chart of stolen boats. And it looks like we've got jet skis that are stolen, motorboats that are stolen, utility or fishing boats that are stolen, inboard boats, I don't even know what that is, that are stolen, and sailboats. And from this Pareto chart, it's obvious that it looks like nearly 1,400 jet ski boats are stolen. And it looks like about 950, somewhere close to 900 motorboats are stolen, and so on. And then it goes down. Sailboats are very unlikely to be stolen. But what's nice about this is that it emphasizes just right off the bat, like what types of boats are likely to be stolen? The jet skis, because they're the tallest. They're associated with the tallest bar here. So this is a particular type of bar graph. You see the bars, they're separated by spaces. They may or may not be separated by spaces in general. But when they're the bars are shown in descending order like this, with the tallest ones first and the shortest one last, that makes it a Pareto chart. Pie charts are also very popular. Now, pie charts depict categorical data as well. So far we've had bar graphs and Pareto charts that display categorical data. Pie charts also display categorical data. But in this case, they're displaying it as slices of a circle, in which the size, of each slice is proportional to the frequency count for the category. And the reason that we have this in this section is that it's showing the distribution of categorical data in a very commonly used format. Our textbook author really does not like pie charts, and we'll talk more about why he doesn't like pie charts when we talk about graphs that are deceiving. But this is so common. People use pie charts all the time that it would be a mistake to not include them in graphs that we should consider to be insightful and enlightening, because we have to infer qualities of data from pie charts all the time. It's something that we should be familiar with. So here is a pie chart for the exact same data. Jet ski boats, I guess. Boats containing jet skis. I actually don't know how jet skis are stored. Apparently those were stolen the most, and then motorboats were stolen the second most, and then utility or fishing boats were stolen the third most, and so on. That's my interpretation of this data without context. So yeah, this is an example of a pie chart. Now, let's look at both of these. It says, which is more effective at showing the types of boats that are stolen most often? Does the pie chart show it to you more easily, or the Pareto chart? Now, because of the way this pie chart is labeled, you know, it could be a tie. You know, half the class might say that the pie chart is great, and the other half the class might say the Pareto chart is great. Who knows? Who knows what the exact proportions would be if I interviewed you in a live or face-to-face class. But typically, pie charts aren't shown like this. Most of the time when you have a pie chart, you have a pie chart and then you have a legend. And there's a little legend that says jet ski boats are associated with this color, and motorboats are associated with this color, and utility or fishing boats are associated with this color. And you have to match the color to the colors on the pie chart, and it takes a while. What's nice about the Pareto chart is that I just look at the bottom. I look at that bottom row, that horizontal row, and I see that jet skis are associated with the tallest bar. So to me, the Pareto chart is much clearer than the pie chart in displaying exactly the same data. The author of our textbook, Mario Triola, would agree. But due to familiarity, you might be more comfortable with the pie chart. So it's definitely a matter of opinion, but we'll talk more about why pie charts are a bad idea, or why they aren't as insightful as other types of charts when we talk about graphs that are deceptive intentionally, or, like most of the time with pie charts, unintentionally. Yes, and that's me pointing out that chart that is more effective. And then the last type of graph that we'll look at is a frequency polygon. This is very similar to a histogram, but rather than having bars representing the frequency of each class, we just plot points on a graph above each class midpoint. And so we have the class midpoint plotted along with the frequency on that vertical axis. and we connect those with line segments, and that graph is going to be called, excuse me, a frequency polygon. So frequency polygons are graphs using line segments connected to points directly above the class midpoint values. Again, it's similar to a histogram, but we use line segments instead of bars. And now the way these are drawn, we always start and end at 0 frequencies. And if you're saying to yourself, our frequency distributions don't often start and end with 0 frequencies, you're absolutely right. But I'll show you how we force our frequency polygon to start and end at 0 frequencies very shortly when we look at an example. And then of course there's variations on this. Instead of a frequency polygon, you could also have a relative frequency polygon with relative frequencies, which could be proportions or percentages on the vertical scale instead of the actual frequencies themselves. So here's a frequency polygon for McDonald's lunch service times in seconds. And so here are our data, excuse me. We've got the service times and the frequencies that are associated with each of those ranges. So this frequency of 11 tells us that in our data set, there were 11 data points that listed the service time that somebody got when they waited for lunch at McDonald's to be between 75 seconds and 124 seconds. So that's very fast, and that's why it's fast food. And then there were 24 people in the data set that waited between 125 seconds and 174 seconds, and so on. So how do you come up with this frequency polygon? Well, what you do at first is you come up with all the class midpoints. Remember how you calculate a class midpoint. It's just the average between this lower class limit and the upper class limit. So you add those together and divide by 2. That's giving you the average of the two numbers. 75 plus 124 divided by 2 turns out to be that 99.5. And you take that class midpoint of 99.5 that goes with this class, and you plot it with the point, or you plot it with the frequency 11. So this is the, you would think of it as an X value of 99.5 and a Y value of 11. Or a service time of 99.5 representing that entire class, and a frequency of 11. And then you do the same thing here. The average of 125 and 174 turns out to be 149.5. You plot the 149.5, the class midpoint for this class, along with the frequency of 24. And that's that point right there. And you do the same thing for all of the other ones. So in practice, what you do is you find the class midpoints for all of these. So by adding these together and dividing by 2, adding these together and dividing by 2, and so on. Or you can take the first one, add them together and divide by 2, and then take that class midpoint and add the class width to get the next class midpoint. The class width, remember, is the difference between two consecutive lower limits. So if I take this 125 and I subtract the 75, the class width is 50. So if the class midpoint for this one was 99.5, to get to the next class midpoint, I just add the class width. I add 50. So I'd be at 149.5. And to get the next one, I add 50 again to get to 99.5. And then add 50 again to get to 249.5. And add 50 again to get to 299.5. And then we're going to assume that that trend continues and add one more 50, add one more class width to get that would-be class midpoint of that class that doesn't exist, that is above 324. And then below this 99.5, we're going to subtract 50 to come up with that would-be class midpoint for the class that would have been before this 75 to 124 second class for our first class. So you take that, you add the 2 extra classes that have 0 frequencies, you plot all of those points, and then you connect them with line segments, and that's your frequency polygon. So this is another way of displaying that data. Rather than displaying it in a histogram, you can display it in a frequency polygon, and it gives you a very good sense of the shape of the data. And we can tell that since that high point is to the left, is kind of low, And if I look at this tail over here on the right, it's long. This is a distribution that's skewed to the right because it's got that long right tail. And we can see all of that with a frequency polygon. Okay, so let's look at an example. I'm going to go back to that old data set of duration times of eruptions of Old Faithful, and we're going to construct a frequency polygon. So the first thing we would do is compute the class midpoints. So I'll take the 125 and the 149, I'll add them together and divide by 2, and I get 137. Now I could do the same to get the next class midpoint and the next class midpoint and the next class midpoint, or I could just keep adding the class width, because those class midpoints are the class width apart from each other. The class width is the difference between two consecutive lower class limits. So you might take this 150 and subtract that 125, and you would see that the class width is just 25. So we're going to add the class width until we come up with class midpoints for all of these classes. So take 137 and add 25, and then add 25 and add 25 and add 25 and add 25, and that's giving you the class width, or excuse me, the class midpoints of all 6 classes. We've got our first one and then the other 5. And then we want to add the class width one more time. So add 25 to that 262 to get 187 to get the would-be class midpoint of the class that would be above this one. And then we also want to subtract 25 from that first class midpoint to get the would-be class midpoint that would be below that one. 137 minus 25 is 112. Next, we want to create a modified frequency distribution, including 2 extra class midpoints. Now, the tick marks for the horizontal axis will be these class midpoints, and then we add that 112 at the beginning, and we add that 287 at the end. And the vertical axis should involve frequencies, should involve numbers between 0 and 35, because the highest frequency class that we have is 34. Oops. I think I'm going to stop sharing here, and then I'll share my paper with you. So I guess I didn't have that written down. That's okay. So we've got those class midpoints. So they were 137, 162, 187, and 212, and then 237 and 262. Those are the actual class midpoints, and then we subtract 25 from this one to get that value, and then we add 25 from this, or to this one, to get this value, and then we write down the corresponding frequencies. So that's 0, that one was 1, and then we had 0 and 0, and then 3 frequency, the frequency was 3 for that class, then 34, then 12, and then back down to 0. So this is kind of like our frequency distribution, but rather than having that range of values in each class, we've listed the class midpoints, and then we added an extra class at the beginning, and we added an extra class at the end. And now we want to take these values and graph them. So we'll have 112, 137, 162. Looks like we've got 8 of them now. 1, 2, 3, 4, 5, 6, 7, 8. And I will just let each of those tick marks represent those numbers, so I'm not going to actually label them here. And the frequencies go up to 34. So maybe we should use multiples of 5. 5, 10, 15, 20, 25, 30, 35. I might as well just put them all in there. Okay, so if this is 112, we want to graph this class midpoint of 112 with a frequency of 0. Then if this is 137, we want to plot that with a frequency of 1, which is not very much at all. Then the next two classes have a frequency of 0. And then the next one has a frequency of 3. And the next one has a frequency of 34. And the one after that has a frequency of 12. And then we go back down to 0. So this is my hand-drawn frequency polygon for this data set. That's how I would do it by hand. I'd have frequencies over here, and these are durations of those eruption times, in seconds. Now let's go back to the PowerPoint. Okay. So we just did this. If we're constructing this by hand, we plot the class midpoints with their frequencies as ordered pairs, and then we connect the points with straight line segments. That's a frequency polygon. Now, if you're asking yourself, well, do I have to do that by hand every time? Well, you're absolutely right. You don't. Most of the time, we don't construct these things by hand, but you do have to do a lot of the calculations by hand. So the first two steps are exactly the same. You're going to create a table, there it is, create a modified frequency distribution that includes the class midpoints for each of these 6 classes, and then we've got a class midpoint for a would-be class before that and a class midpoint for a would-be class after that, and with a frequency of 0. And then once you do that, you would want to go to Excel and enter that data manually. So let's look at Excel and do just that. Now I think I may have already saved this data somewhere. There it is. Old Faithful frequency data modified. There we go. So these are my class midpoints with the extra class midpoint at the beginning and the end, and the corresponding frequencies. So all I do is I just highlight these 2 columns in Excel, and then I go to Insert. Now I don't know if you have to do this in Microsoft Excel, MS Office, the MS Office suite when you're on a PC, but I'm on a Mac, and for some reason when I'm on my Mac and I want to plot sets of data like this, I have to start by plotting a scatter plot first. So I go here to the scatter plot image and I select the first one, and it just plots the points. And then I wanted them to be connected with line segments. So now I'm going to go back to Insert, and rather than trying to find some way to take this and connect all of these values with line segments, I'm going to go up to here to these line graphs. I'm choosing a 2D line graph, the very first one, and it makes a line graph for me. Now, I probably wouldn't leave it like this. I would change the title. These are duration of eruptions of Old Faithful, and this we know to be a frequency polygon. That's what we were creating. And then I would probably also label the axes. So I would go to Chart Design, add chart element, and let's do axes titles, primary, horizontal. So this axis represents the duration of each of those eruptions in seconds. And then I would go here and then go to primary vertical, and those are frequencies. I wish I could see it not sideways, but that's okay. We can make do. All right. And then that's our graph. That is our frequency polygon. So I'm going to show you our PowerPoint again. Now, I originally had this frequency polygon with a white background, like the one that you saw in Excel, but it was blending in too much with the background of the PowerPoint slide, so I gave it this dark background, but you get the idea. That is the frequency polygon for those duration times. We start at 0, we go up to 1, then we're at 0 and 0 again. Then we are at 3, then the frequency jumps up to 34, then it goes back down to 12, and then back to 0. And then we can also talk about relative frequency polygons. These are McDonald's relative frequency polygons and Dunkin' Donuts relative frequency polygons for lunch times, lunch service times at Dunkin' Donuts and McDonald's. We see from this picture that Dunkin' Donuts has a much shorter lunch service time. But I mean, they serve donuts and McDonald's serves food, so you would expect that. They serve like meals with protein, whereas Dunkin' doesn't tend to, not for the most part, not at lunch. Anyway, so that's a relative frequency polygon. Okay, so I'd like to just summarize now. Let's go to the very beginning. We had 7 types of graphs that are enlightening. First, we've got the dot plot. So that's a plot with a horizontal axis and a dot for each data point. Then we have a stem plot, which kind of does the same thing as the dot plot, but it just does it sideways. And instead of representing each data value with a point or a dot, stem plots separate each data value into a stem and a leaf, and the leaves are listed in ascending order on the other side of the stem, and you can see the entire data set that way. Then we've got time series graphs. So if you have some number of values that change over time, if we graph that, we call that a time series graph. And there's an example of how to do one of those or how to create one of those in Excel in one of the videos. Then we've got bar graphs. These are for categorical data or qualitative data. All the bars have equal widths, doesn't matter if they're spaces. Pareto charts are special types of bar graphs. They're bar graphs where the tallest bar comes first and the bars are arranged. The tallest one is first and the shortest one is last, and they're going in ascending order of height, or descending order of height, excuse me. Then we've got pie charts. Mr. Triola, the author of our textbook, is not a fan, and we'll talk about why in the next video, but they're so popular that we should be familiar with what they look like. When we're looking at this categorical data for the number of boats that are stolen, or the types of boats that are stolen most often, the Pareto chart is more insightful. It's more effective at conveying that than the pie chart, in my opinion, and in Mr. Triola's opinion. And then the last type of diagram we have, or graph we have, that can be insightful is a frequency polygon. And that is just like a histogram, really, but instead of having a class of values that's defined by a range of values, we use the class midpoints, and we plot the class midpoint with the corresponding frequency, and then we add a point at the beginning at 0 with a 0 frequency, and we add a point at the end with a 0 frequency to give us that frequency polygon. All right. That's it for right now. I will see you in the next video.